last lecture we have discussed the Cauchy integral theorem, and the Cauchy integral theorem says if the function is analytic in a simply connected domain D, then for every simple closed curve C lying inside the integral of the function f z d z along this curve C will be 0. This is the Cauchy integral theorem. And as a consequence of this, we have already proved as a consequence to this problem that the line integral is independent of path. If the function f z is analytic, if the function f z is analytic in a simply connected domain D, then the integral of f z, dz is independent of path, in D. That is, if D is this simply connected domain and function f is analytic at each point, then if we independent of one means if we picked up the 2 point z1, z0 and z1 suppose, then integral of this function f z dz from z0 to z1 will depends only at the point z1 and z0, but does not depend on the path of integration. Whatever the path you choose, joining these 2 points, the value of the integral will remain the same. So, this comes out as a consequence of the Cauchy integral theorem or an application to Cauchy integral theorem. So, this much. Then further deformation of path is also another use from Cauchy integral theorem. One can derive deformation of path. The deformation of path we mean, suppose we have this curve, say z0 and z1 not be the 2 points, and this is the path of integration C. Since function f is analytic inside this domain D, which is simply connected domain, then the value of the integral f z will depends only the point z0 and z1 independent of the path. It means, if we take any other path joining the z0 to z1, then the value of the line integral will not change. So, we can think that this C path, this is suppose C star, then if I consider infinitely many paths joining point z0 to z1 in such a way that it keeps on reducing and going up to the C. In this process, the point z0 and z1 is fixed, means the path will always join the z0 and z1, but it approaches towards C, and the point through which this curve passes where the function should be analytic. So, if the function is analytic throughout this domain, means whatever the path you choose, it will independent of the integral will independent of the path. So, the C star when it touches to C, the value of the C star along C star and value of along integral of the function along C will remain the same, and this is called the deformation of the path. This is, it means if the path is given in a very uncomfortable way, then one can transfer it C star to a comfortable path, provided the initial and terminal points are intact and the function is analytic throughout this process. So, this will give the let us see the example for this. Suppose we have this curve, let us Okay, we will see the example afterward. Let us see first some. Now, one more result which we have mentioned earlier, the existence of indefinite integral. This we will just state without the proof. What this says, if the function f z is analytic in a simply connected domain D, then there exists an indefinite integral capital F z of small f z in D such that f prime z equal to f z, which is analytic. F is analytic. So, f prime z is also analytic in D. And for all path in D, joining any 2 points z naught and z 1 in D, the integral f z d z z naught to z 1 can be evaluated with the help of this t f of z t d z by dt when t varies from t naught to t 1, t varies from a to b, t varies from a to b and t lying between a to b. Z naught is corresponding to point t of a, z naught which is z of t is a, and z 1 correspond to the point b. So, this is so we can get the value of this line integral in terms of the definite integral from a to b f of z t dt. We have already used this part, but the existence of is guaranteed because of this result. If function is analytic, then definitely the derivative of this function, this integral will exist and equal to the f prime antiderivative. Proofs we are not giving because this is okay. Now, we have seen the Cauchy integral theorem in case of a simply connected domain, but if the domain is not simply connected, then also we have a Cauchy theorem for multiple connected domains. What we do is here we convert the multiple connected domain into a simply connected domain first and then apply the Cauchy theorem for the simply connectedness. So, the result is Cauchy's theorem for multiple connected domains. Okay. Cauchy theorem, suppose we have a function, let f z be f z is analytic, let f z be analytic in a domain D star that contains the domain D and its boundary curves. Boundary curves C1 and C2 as in figure. Okay. Figure is that suppose this is our D star, this is our D, contains between the two curves C1 and C2. In between, this is the domain D, and D star is the domain which contains the points of D as well as the point of the boundaries C1 and C2. So, basically D star is a multiple connected domain, it is not a simply connected domain, okay? Multiple connected domain. So, D star is a doubly connected or multiple doubly connected domain, is it not? Because this has a two boundaries and this portion is not there, simply connected. Then this theorem says, then the Cauchy theorem for the multiplication says, then Cauchy theorem say give that integral along the curve C1 of the function f z d z will be the same as integral of the function f z d z along the path C2, where both integrals are taking either counterclockwise or clockwise. Counterclockwise or clockwise means same direction, both are taken. Okay. So, this is the Cauchy theorem for a multiple connected, that is the value of the line integral along the outer boundary is the same as the value of the line integral along the inner boundary when the direction is the same. Okay. So, let us see C1 and C2. Okay. Then what we say is okay. Proof is simple. Suppose we have a multiple connected domain which has these two boundary, say C1 and C2. So, this is our C1 and here is C2 and D is this domain with it. Now, this is the domain D star, which is D union the boundary points C1 and C2. So, this is our domain D. Now, let us convert this thing into a simply connected domain by putting the two cuts along this. So, this is our one cut. So, if we start through this way, come back up to here and then go from here along this direction and then come back this way again this direction, then you are getting one domain, say D1. Then similarly, when you are going along this direction, come back through this way and again this direction up to here, then come back and get like this. So, we get D2 another. It means the D star now has been break up into the two domain D1 and D2 and both are simply connected domains. So, this is our, now here when the path C1 and C2 are same, is it not, then direction is the same, but here the direction reverses. Okay. So, that we will take care for it. So, what we have, the D star is nothing but the D1 union D2 and both D1 and D2 are simply connected domains. So, we can apply the Cauchy theorem for this. Therefore, the line integral of the function f z d z along the path this, that is this value C 2, this is C 2. So, if I go along this path C 2, come back this way and then come here. So, let us see the path this as C 1, let us C 1 dash or C dash, path C dash, this along over the curve, over the domain D1, and then the integral of the function f z dz over the domain D2, where the boundary is this C2 plus this and going like this. So, when we consider this integral along this closed boundary and function is generated, the value of this will be 0, value of this will be 0 and total is 0. So, we get from here is the integral along C dash f z dz is the integral minus times of integral along f z dz C double dash. Okay. The value of the integral along these curves, that is this side and this side get cancelled. Similarly, this side and this side are opposite. So, the value of the integral along these two cuts will not contribute, it will be 0. So, we do not have the value either added or subtracted over the arc this C 1, which we call it as C 1 dash delta, and here is C 2 dash C double dash delta, this one. Okay. So, we do not have. Now, C dash is this curve where this direction is taking in this way, that is the direction is opposite to the direction which we are taking earlier. C 1 is this direction and it is opposite, this is going opposite of this. So, this becomes the minus of C 1. So, this is equal to minus of C 1 f z dz equal to minus. Now, C 2 dash, C double dash is the curve along this integral along this curve. So, the direction is the same as C 2, basically it is a part of the C 2 plus this C double dash, but these are all 0. So, except C 2 it will come. So, C 2 plus this curve, C 2 plus this. So, basically this we are getting this C 2, I am so this one C dash is completely this 0. So, C dash is what we are getting this curve here C 2 plus this C 1. So, here C 2 will also come, C 2 f z dz part of it in D2 in D1, and this will come the C 2 in D2 okay, in that D2 plus this portion which is the opposite of this. So, opposite of this means plus of this C 1 f z dz, because this is opposite to this, So, it is C 1. So, part in D2, this is also in D1. So, this is the portion lying in D1, this portion is lying in D2. So, if we combine these two transfer, then this is the total C 1. So, this implies that integral along C 2 f z dz is integral along C 1 f z dz. That proves the result. Okay. Is it okay? Or just I will again repeat what we did. We wanted to prove that integral of the function along the outer boundary is the same as the integral along the inner boundary when the direction is taken same. So, what we did, we have made the two cuts. So, by making these two cuts, the entire domain D star is divided into two parts, D1 and D2. Now, D1 consists of a part of the C2 arc and the arc C1 dash star dash, these arc. Then D2 consists, the boundary consists of a part of C2 and C double dash arc. So, the value of this integral is 0, means the value along this plus value along this must be 0. Similarly, the value of this means value along C2 and these two are 0, but these two are opposite, these two are opposite and the same path, function is same, so the value will not contribute. Therefore, the value of the integral along outer boundary is the same as the value along the inner boundary, and that proves the result for it. Okay. So, that is now this can be extended in general. Suppose there are, this is our domain where there are many holes are there, say this holes. Okay. So, it is a multiple connected domains and the boundaries are C1, here C, this is the boundary is say C1, this is the boundary is say C2, this is the boundary is C3, same direction. Then the line integral of the function f z d z along C will be the same as the line integral of the function f z d z along C1 plus line integral of the function f z d z along C2 plus the line integral of the function f z along C. Now, C1 and C, the direction of C and direction of C1, C2, C3 must be the same, either both same clockwise or maybe the anti-clockwise, it hardly matters, and this shows. Now, before going for this some more examples here, let us see the first, which is interesting example to find the value of this integral, because it will be used dz z minus z naught to the power m dz over the C, where C is the circle, any closed curve circle mod z circle z minus z naught is equal to say r. Okay. This we wanted to show, prove it. So, it is given z minus z naught is r e to the power I theta, where theta lying between 0 and 2 pi, because it is a circular path centered at z naught with a radius r. So, any arbitrary point z, if I take it, then z can be written as z naught plus r. So, dz will be equal to r I e to the power I theta d theta, and therefore, the integral z minus z naught to the power m dz along this path C will be z minus z naught is r to the power m e to the power I m theta divided by then dz is r I e to the power r I e to the power I theta d theta. Okay. Now, when we and value is 0 to 2 pi. So, basically it becomes I r m plus 1 integral 0 to 2 pi e to the power I m plus 1 theta d theta, is it not? And this value will come out to be I r m plus 1 e to the power I m plus 1 divided by I m plus 1 and limit 0 to 2 pi theta. So, the value of e to the power I some constant theta 2 pi will be 1, and at the point 0 is also 1. So, the value will come out to be 0 if m is different from minus 1. But when m is minus 1, then we have to evaluate this integral separately, and we get z minus z naught along the path C, where the C is this circle z minus z naught is r. Okay. So, if I evaluate this, the value will come out to be z minus z naught is r e to the power I theta, dz is equal to r I e to the power I theta d theta, and 0 to 2 pi, the value will come out to be 2 pi I. So, this result says the value of this integral will be 0 when m is different from minus 1 and equal to 2 pi I when m is equal to minus 1. This will be useful. Okay. Now, as we have seen that few examples, we will go for this. Okay. suppose we have evaluate the integral z over 1 plus z square dz along the path C, where C is the upper, where C is the upper, C is the upper semicircle, mod z plus half equal to upper semicircle is the upper part of the semicircle z plus 1. Okay, like traverse in the anticlockwise direction. Using deformation of path. Deformation of the path. Now, if we look this circle, the circle is basically centered at minus half with a radius half. So, it will be this path and traverse in the anticlockwise direction. So, we are moving in this direction. Clear? Now, this is our 0. The function f z, which is z over 1 plus z square, cease to be analytic, ceases to be analytic, that is, it is not defined, all derivatives does not exist, cease to be analytic at the point where the denominator is 0, z equal to plus minus I, and plus minus I will be somewhere lying here. This is plus I, this is minus I. So, it does not fall at any point on this circle, on the path of integration. This is path of integration. Therefore, if I join these 2 points, I kept it as it is. This is 0, this is 1. If I kept these 2 points intact and draw the curves joining these 2 points, then the integral along this curve will be the same as the integral along this curve, because the function is analytic throughout all these points and the joint initial and terminal point are intact. So, if I keep on changing, then I will take only the simplest path, and simplest path is this from 0 to 1 along x axis. So, here choose x axis and x axis the path C, this is the path C, can be replaced by the line segment OA, this is suppose AO, this is A, OA along x axis, whose parametric equation is zt equal to xt plus by t. So, xt, that is t, by is 0. So, t varies from minus 1 to 0. Oh, sorry, 0 to minus 1. Why 0 to 1? Because the direction is taken in anticlockwise, 0 to minus 1. Okay. So, if I take zt equal to t, then t varies from 0 to say minus 1, this is minus 1, I am sorry, this is minus 1, then 0 to minus 1, then integral along this path C can be replaced by the integral of the function along the x axis, along the line segment OA, which is on the x axis joining O to A. So, this integral I reduces to the integral z equal to t. So, replace t over 1 plus t square dt and minus 1 to 0. Okay. And this value can be easily integrated, because 1 plus t square, if I put it to be t, then we are getting this value is coming to be half log 2. So, by using the deformation of the path, one can easily get the integral, or one can change this path of integration suitably and get the result. Okay. Now, let us take few other evaluate using the Cauchy theorem for multiple connected domains. Okay. Evaluate this integral I along the path C of the function 3z minus 1 over z cube minus z dz, where C is the contour closed curve as shown in figure A. The figure is suppose we have this curve. C is the path of integration like this. This is our C. This C, which encloses the point minus 1, 0 and 1. These are the points. We are interested in finding the value of the line integral of this function along this path, along this closed curve. C is the closed curve. Now, if I look the domain which is inside this closed curve C, then you see the function f is not analytic at this point. Since the function f z, which is 3z minus 1 z square minus 1, cease to be analytic at the point z is equal to 0, z equal to 1 and z equal to minus 1. So, these are the 3 points where it ceases to be analytic, means the function is not defined at this point, because the denominator vanishes at this point. Okay. So, we have to remove this point, because the function is not analytic. So, if I consider the domain which is free from these points, that is 0, minus 1, 1, just draw these circles centered at 1, centered at 0 and centered at 1, minus 1. If I draw these curves which are say C 1, say C 1, C 2, C 3, these are the closed curve which encloses the point 1, 0 and minus 1 respectively. So, if I look this domain, then this domain and the boundary is this C, this is the boundary of this domain. Then this entire domain becomes basically a simply connected, if I drop this multiple connected, because it has a gaps, these holes are there, 3 holes are there. So, this entire domain is a multiple connected domain. So, by Cauchy theorem, the value of the function f z, this function now 3z minus 1 over z cube minus z, this function, if you take the function is not analytic at this point. So, if I remove this point, then for the rest of the function is analytic. So, by Cauchy theorem, the value of the integral of this curve dz along the path C is the same as the value of this function along C 1 plus value of the function along C 2 plus value of the function along C 3, is it not? So, we get this. Now, C 1, C 2, C 3 let us compute separately. So, let it be 1. Okay. Now, what is our C 1? C1 is that first is function f z, this is 3 z minus 1 z z square minus 1. So, we can if we write the partial fraction for this, the partial fraction will come out to be 1 by z minus 2 by z plus 1 plus 1 over z minus. This is just simple z minus z, and write down the partial fraction, we get this. So, integral along C1 f z dz, this is equal to, now integral along C1, yes. What is the C1 is? Integral along C1, this is integral along C1 1 by z dz minus 2 times integral of this along C1 plus integral of this along C1. But what is C1? C1 is this curve which encloses the point z equal to 1 and 0 and minus 1 is outside. So, if we look the function f z, which is 3 z minus 1 over z z square minus 1. So, in this case the function f z, which can be written as 3 z minus 1 over z z minus 1 z plus 1. So, if we look this function z plus this point z plus 1, this point is no longer in this point z equal to 0. 0 is not included inside C1. So, the value of this integral will be 0, because it becomes analytic, is it not? 1 by z dz, z equal to 0 is the point, which is singular point, but inside the C1 0 is not there, 0 lying outside. So, function f z 1 by z becomes analytic. So, integral Cauchy integral theorem says the value of this integral must be 0. Then z plus 1, z equal to minus 1, again z equal to minus 1 lying outside. So, again the value will be 0, but for this z equal to 1 lies inside. So, once it inside lie, then with the value of this integral is nothing but the value of dz over z minus 1. But we have already seen one example where the value is coming to be this, z minus z naught to the power m, the when m is minus 1, the value is 2 pi I. So, the value of this integral will be equal to 2 pi I. Okay. Then integral along C2 f z dz. In a similar way, we can say C2 1 by dash g dash to dz over z plus 1, then plus dz over z minus 1. Where is the C2? C2 is the point which encloses 0. So, minus 1 and plus 1 is out. So, it means z plus 1 or z minus 1, 1 by z plus 1 or z minus 1 becomes analytic, So, these are 0, these are 0, and this z equal to 0 will give only the value which is just if you compute z equal to all e to the pi theta etcetera, the value will come out to be 2 pi. So, here the value will also come out to be 2 pi. Okay. Now, third case, when it is integral C3 f z dz. C3 is, now this is our z C3 z plus 1. So, z plus 1, this will give the value. So, this will give the value, rest are 0 except this, others will be 0, and this is nothing but minus 1 plus 1. So, the value will come out to be minus dz over z minus minus 1, that is the same as z minus z naught. So, again the value will be 2 pi. So, it is minus 2 pi I and multiply by 2, is it not? So, this is minus this, sorry, here this. So, it is equal to minus 4 pi I. So, what we get it here, the integral along the closed boundary. So, we get according to the first. So, first says, so from first integral of this function along the outer boundary C is the sum of the integral along C1, C2, C3. Therefore, the sum value will be 2 pi I plus 2 pi I minus 4 pi and that comes out to be 0. So, that will be the one. Okay. So, this will be our. Now, let us take one more problems, that is Cauchy. Okay. Now, we have another application of the Cauchy integral theorem. Cauchy integral theorem is the Cauchy integral formula. The Cauchy integral formula, this is the consequence of the Cauchy integral theorem. It is a consequence of the which says the value of the function at a point z naught inside the domain D, where the function is analytic, can be computed. So, what is said Cauchy integral? Let f z be analytic in a simply connected domain, D, in a simply connected domain D, then for any point z naught in D and any simple closed path C in D that encloses the point z naught, the value of the integral f z over z minus z naught dz along this path C is equal to 2 pi I times the value of the function f z naught. The integration is being taken, taking counterclockwise direction. So, it means if we are interested finding the value of this is like this. If suppose f z be is analytic in a simply connected domain D which has a point z naught inside this. Take any simple closed curve path C in D which encloses the point z naught. Then the value of this integral f z over z minus z naught along the path C will be 2 pi a times the value of the function h z naught. So, in other words, you can say that if we are interested finding the value of a function f at an arbitrary point z naught in a domain D where the function is analytic, then you simply calculate the integral of f z minus f z over z minus z naught along any simple closed curve C which encloses the point z naught, multiply this by 2 pi I. Sorry, divide by this 2 pi I. Divide this by 2 pi I. Then this will give the value of the function at a point z naught. Okay. The proof of this we will see the proof, but let us see the advantage of this is. The advantage is that suppose we wanted to calculate the say integral of this function, say z cube minus 6 over say 2 z minus I. Suppose we wanted to compute this integral, then what we do is, and C is the, where C is the circle mod z minus half, and this is the I by 2, Z naught is inside the circle, Z naught by I by 2, a central is I by 2 with a radius say 1. Okay. So, if we consider this circle centered at I by 2 with radius say 1, okay, with radius say 1, then what we get is that this function z cube by 6 over 2 z minus I cease to be analytic at z equal to I. So, but the function z cube by 6 here, the function f z which is z cube by minus 6 by 2, this function is analytic inside the curve C, and it has a point I by 2 inside. So, as a whole the function is not analytic at z equal to I by 2, but if you look, this function is analytic inside the curve z minus I by 2 is less than equal to 1, clear. And what this theorem says is, if the function f is analytic inside the domain D or inside the curve C, then the f z over z minus z naught, the value of this integral along curve C will be this much. So, basically this is can be written like this: the integral C z cube minus 6 2 z minus I dz can be written as integral z cube minus 6 by 2 over z minus I by 2 dz along the path C and C is this circle. So, C is the circle, z minus I by 2 is 1. Therefore, by this Cauchy integral theorem, the value of this integral will be 2 pi I times the value of this integral is value of the function at z naught, value of the function f at the point z naught. Z naught is what point? Z naught is I by 2, I by 2. So, this comes out to be 2 pi I z cube minus 6 by 2 at the point z equal to I by 2. And if you compute z by this, the value will come out to be say minus pi by 8 minus 6 pi I. Okay. So, this is what another examples also. Let us consider the curve, find the integral C z square plus 1 over z square minus 1 dz along the path C, where the direction is taking counterclockwise, where C is given as in figure. Suppose we have the first case, C is this circle, this is the 0, here is minus 1, this is 1. Suppose this is our C. C is this curve, closed curve surrounding the point 1. So, if we take the curve C surrounding this point, then what happens? The function z square plus 1 over z square minus 1 cease to be analytic at z equal to 1. But if we consider this function as the integral z square plus 1 over z plus 1 divided by z minus 1 dz. Suppose I rewrite this function into this form along the path C, then this part of the function, the numerator, is analytic throughout this, and this function which is analytic inside the C and having the point 1 inside this curve C, C encloses the point 1. So, apply the Cauchy integral formula. The Cauchy integral formula says the value of this will be 2 pi I times the function f z at z is equal to z naught, that is 1. So, you can find out the value of this integral and get this value comes out to be 2 pi I, because 1 plus 1 get cancels 2 pi I. Now, in the second case, if suppose I second part, if I shifted this curve and we get this curve, suppose I shift it here, say minus 1 1, and I shift it like this, say like this, okay. This curve C, this is the curve C, where minus 1 included and 1 is outside. So, the same integral along this curve z square plus 1 z minus 1 z plus 1 dz, we can rewrite like this z square plus 1 z minus 1 is there. So, z minus 1 divided by z plus 1 dz along the path C, because the function is throughout analytic except the point z equal to minus 1. So, that point I am taking below. So, it is f z over z minus. So, this function is analytic inside this curve C. So, by integral Cauchy integral formula 2 pi I times the value of this at z is equal to minus 1, and that value will come out to be minus 2 pi I. And suppose it encloses both the points, then you apply the Cauchy integral formula, integral theorem for the multiple connected domains, and the value will. Or if we take this integral minus 1 to 1 and this is the curve C, then the value of this integral f z will be 0, because the function is throughout analytic. So, the value will come out to be 0. So, that is the advantage of computing the integrals by just manipulating the whole function. Thank you very much. Thanks.